Hello everyone. We are here to present our AI group project on vehicle identification for traffic safety. Problem statement. So, our problem statement basically is that there's a need for an automated system that can detect and track vehicles for managing traffic. In our day-to-day lives, we see many accidents happening, and the majority of these accidents are caused due to overspeeding, not wearing helmet, and improper cycling. So we have tried to come up with a solution to solve this problem. Objective. Here we have designed a model using YOLO V8 which will identify cars, buses, cycles, etc. And this model also tracks the vehicle and estimates speed. It determines whether the vehicle is overspeeding or not, and whether the driver on a motorbike is wearing a helmet or not. And in case of cycling, it will detect whether the driver is holding the handle. Here we have two main assumptions. The first one is that the model can display only one vehicle at a time, and the second one is that the model can only identify cars, buses, trucks, motorbikes, and bicycles. Basically, roadside vehicles. Our agent is a goal-based agent, and it is designed for real-time traffic monitoring. This agent uses YOLO V8 for object detection and DeepSort for tracking, as well as OpenCV for speed calculation.
So for our project, the hardware we have used are Arduino Uno, which is a microcontroller, 20 by 4 LCD display to display the output, I2C chip to connect Arduino to LCD display, external power supply, and a camera. The software which we have used are Ultralytics YOLO V8 model for detecting the vehicles, OpenCV library for real-time computer vision and image processing, Arduino IDE for setting up Arduino, NumPy, Python, and DeepSort for tracking the vehicles. So the most important performance measure which we have considered is to correctly identify vehicles and display warning messages. If the person driving the vehicle breaks the rules, the agent should have a quick response time and a clear display on LCD screen. The environment which you have considered is any roadside environment. It can be a highway intersection or a traffic signal. The actuator is an LCD display, and the sensor is camera. So the input we have given is live or recorded video capturing traffic scenes with vehicles like cars, cycles, and buses. The output should be that the model should identify each vehicle, and it should also highlight the vehicles which are overspeeding, have drivers without helmets, or cyclists not holding the handle, and it should show a warning message or violation status using Arduino LCD screen.
As said before, for the hardware, we are using Arduino Uno LCD display and I2C chip. We can make the connection without the chip, but we'll need to make 16 connections. So to avoid so many connections, we are using the chip, because then we'll only need to make 4 connections. Now the Arduino is coded using Arduino IDE, which is written in C++. In that we use two libraries, that is Liquid Crystal I2C to display the text on the LCD display, and Wireheads for the communication between the devices. The main code is written in Python, and it uses YOLO, OpenCV, and DeepSort. YOLO can only detect and identify the object, but it cannot track them across the frames. For tracking, we use DeepSort, and it does this by giving a unique ID to the object, and so the tracking becomes simpler. OpenCV is used for calculating the speed, and this is done with the help of the unique ID provided by DeepSort. And with this unique ID, the vehicle is tracked among different frames. The distance of the vehicle between the two frames are calculated, and using the formula speed is equal to distance by time, the speed is calculated. This calculation is done across various frames to get a more accurate speed value. The Python sends the data to Arduino using serial communication, that is 1 bit at a time, and once the Arduino receives a message, it gives the message to the LCD display. This flowchart explains how the code works. Once the code starts running, the system gets initialized and it is displayed on the LCD display. When a vehicle is detected, the speed is calculated using OpenCV, and the speed along with the vehicle type is displayed. If the speed is over a predefined limit, then overspeeding is also displayed on the LCD display. Along with this, in the case of a cycle, if the rider is not holding the handlebar, then a warning is displayed, and in the case of a bike, if the rider is not wearing a helmet, again a warning is displayed. Now this is the working video.
As you can see, this is case 1 of a car. When it overspeeds, the box turns red, and this is in the LCD display. This is case 2 of a motorcycle, where there is a message displayed to wear a helmet, and this is the output on the LCD. Here overspeeding is displayed. This is of a bicycle, where a person riding without holding handlebar. As you can see, the message is displayed on the LCD. Here we have provided pictures. This is the output on screen, and this is the same output on the LCD display. Here you can see there is a message of please wear helmet. Here it's the same thing for a car. Here we have provided for a bicycle. Again, a message is displayed on the screen. Please, a person riding without holding handlebar, and on the LCD display, it displays a message saying us to hold a handlebar.
Here I'll be covering the algorithms used. Number 1, YOLO V8 object detection. YOLO is a real-time object detection algorithm. Each detection includes a bounding box, class ID, and conference code. In this project, YOLO detects vehicles like car, bus, truck, motorbike, train, and person to detect driver or rider, and helmet to detect if person is wearing a helmet or not, and hands to detect if cyclist is holding handle. Number 2, deep sort for object tracking. It assigns unique ID to objects and tracks them across frames even if they move or overlap. In this project, deep sort helps track each vehicle individually with a consistent vehicle ID, tracks the same person riding a bike, and computes speed using OpenCV. And our learning includes software solutions are better understood via hardware implementations, learned how to use hardware interfacing and stimulators like Arduino IDE and Tinkercad, learned how to connect and program an Arduino to work with real-time data from a computer vision system, and then gained practical experience by displaying messages on LCD. Our future plans include this system can be improved by adding an automatic number plate recognition to help identify vehicles that violate rules, and then this system can also be enhanced to work reliably at night or during bad weathers. A mobile app can also be created to display live feeds, track violations, and provide real-time alerts. This is our team management, and this is the references we used for our project.
Thank you.